To accurately calculate the available fault current on the secondary side of a transformer, it's crucial to use the correct formula. The formula you were initially using is designed to determine the fault current at the primary side of a second transformer within a system. However, to find the fault current on the secondary side, a different approach is needed. The correct formula is as follows: I subscript SC, sec equals I subscript SC, pi times V subscript pi divided by V subscript sec times 1 divided by 1 plus F, where I subscript SC, sec represents the available fault current at the secondary side of the second transformer in the system. I subscript SC, pi is the available fault current at the primary side of the second transformer in the system. V subscript pi is the primary voltage of the second transformer in the system. V subscript sec is the secondary voltage of the second transformer in the system, and F is the F factor of the second transformer in the system. Let's break down each component and its role in the calculation. I subscript SC, pi, the available fault current at the primary side, is the starting point. This value represents the amount of fault current that the primary side of the transformer can supply during a short circuit condition. It's typically provided by the utility or calculated based on the upstream system impedance. V subscript pi, the primary voltage, and V subscript sec, the secondary voltage, are the voltage levels on the primary and secondary sides of the transformer, respectively. These values are essential for voltage transformation and impedance calculations. The F factor is a crucial element that accounts for the transformer's impedance and its impact on the fault current. It's calculated using the formula F equals primary side fault current times primary voltage times 1.732 times %C divided by 100,000 times kilovolt amps. The %C represents the transformer's impedance typically found on the transformer's nameplate. It indicates the percentage of voltage drop that occurs when the transformer is fully loaded. Kilovolt amps represents the transformer's rating in kilovolt amps. Now let's apply this formula with the values you provided to demonstrate how it works in practice. Given an I subscript SC, pi of 20,345 amps, a V subscript pi of 480 volts, a V subscript sec of 208 volts, and an F factor of 266,395.8 divided by 100,000, we can plug these values into the formula. I subscript SC, sec equals 20,345 amps times 480 volts divided by 208 volts times 1 divided by 1 plus 266,395.8 divided by 100,000. Simplifying the equation, we get I subscript SC, sec equals 20,345 amps times 2.3077 times 1 divided by 3.663,958. Further simplification yields I subscript SC, sec equals 46,947.8 amps divided by 3.663,958. Finally, we arrive at I subscript SC, sec equals approximately 36,739 amps. This result aligns with the value you obtained from your cheat sheet, confirming the accuracy of the formula. It's important to note that the F factor plays a significant role in reducing the available fault current on the secondary side. The higher the F factor, the greater the reduction in fault current. This reduction is due to the transformer's impedance, which limits the amount of current that can flow during a short circuit condition. Understanding the underlying principles behind this formula is crucial for accurate short circuit analysis. The available fault current on the secondary side is essential for selecting appropriate protective devices, such as circuit breakers and fuses, to ensure the safety of the electrical system. If the calculated fault current exceeds the interrupting rating of the protective device, it could fail to interrupt the fault, leading to equipment damage, fire hazards, and potential injuries. In addition to using the correct formula, it's also important to consider other factors that can affect the available fault current. These factors include the source impedance of the utility, the impedance of conductors and other equipment in the circuit, and the presence of any motors or generators that can contribute to the fault current. Furthermore, it's essential to use accurate values for the transformer's impedance and kilovolt amps rating. These values are typically found on the transformer's nameplate. Using incorrect values can lead to significant errors in the fault current calculation. When performing short-circuit calculations, it's also important to follow industry standards and best practices. These standards provide guidance on how to perform accurate and reliable calculations. They also specify the minimum requirements for protective device coordination, which ensures that the protective devices operate in a coordinated manner to isolate faults quickly and effectively. Furthermore, regularly review and update your short-circuit calculations to account for any changes in the electrical system. Changes such as adding new equipment, modifying existing circuits, or changing the utility source impedance can affect the available fault current. By keeping your calculations up to date, you can ensure that your protective devices are properly sized and coordinated to protect the electrical system. In summary, accurately calculating the available fault current on the secondary side of a transformer requires using the correct formula, understanding the underlying principles, considering other factors that can affect the fault current, using accurate values for transformer parameters, following industry standards and best practices, and regularly reviewing and updating your calculations. By following these guidelines, you can ensure the safety and reliability of your electrical system. Remember that accurate short-circuit analysis is essential for protecting equipment, preventing fire hazards, and ensuring the safety of personnel. Take the time to understand the calculations and consult with qualified professionals if you have any questions or concerns. This will help you make informed decisions about the selection and coordination of protective devices, ultimately leading to a safer and more reliable electrical system. Also, consider investing in specialized software tools that can automate the short-circuit calculation process. These tools can significantly reduce the time and effort required to perform calculations and can also help to identify potential errors. However, it's important to understand the underlying principles behind the calculations, even when using software tools. This will allow you to verify the results and ensure that they are accurate and reliable. Furthermore, consider attending training courses or workshops on short-circuit analysis. These courses can provide you with the knowledge and skills needed to perform accurate calculations and make informed decisions about protective device coordination. They can also help you stay up to date on the latest industry standards and best practices. Finally, remember that electrical safety is paramount. Always follow safe work practices when working on or near electrical equipment. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves, and energizing circuits before working on them. By prioritizing electrical safety, you can protect yourself and others from potential hazards. By using the correct formula, understanding the concepts, and following industry best practices, one can confidently calculate the available fault current at the secondary side of a transformer. This will enhance the safety and reliability of the electrical system, preventing potential damage and ensuring the protection of equipment and personnel. The accurate determination of available fault current is not just a theoretical exercise, it is a practical necessity for electrical engineers, technicians, and anyone involved in the design, installation, and maintenance of electrical systems.